So my name is Ausmarton Fernandes. I've been working with Scala for, not very long though. So category theory is something which I've always, I did do a bit of math in university, but then I always felt that there was something about category theory which was, so some parts of it which felt very familiar, and there were some parts of it which felt quite a bit difficult to comprehend. So I just kind of made this as a presentation as a part of what I've learned as I was going through category theory and in practice. So these are this is what I had in plan for today. Why category theory basically, and why I found it a bit difficult to understand at the beginning, and some basic terminology around it. I'm not really going to cover things like monads and Kleisli and natural transformations. I'd probably do that as a separate presentation later. So today I'm just going to cover things like monoids, functors, and applicative functors. That's about it. So yeah, so this is I'm not really a mathematician. It's just a programmer's point of view, and I know in the abstract which I had sent out, there was a thing about Cats and Scalaz. I don't really have anything about Scala Z in here, but I've got some examples from Cats and how we would use it in standard Scala, and this is just an introduction to category theory. So yeah, why category theory? So one of the things that category theory tries to do is create abstractions in various parts of mathematics, like set theory, group theory, and topologies, and find patterns in there. It's pretty much what we would do as programmers, find abstractions and redefine, more concrete implementations of that, but more in terms of, generics or, the patterns which we can find across all these different branches. And composition, of course. So that's again something that we do use on when we write software. It's all about function composition. It's a similar thing when moving from, let's say, imperative style programming to functional programming. We would try to write functions which then we compose together to create larger programs. As I said, it's about finding patterns in things and then finding patterns in those patterns. We'll get to this when in the coming slides, and yeah. So yeah, this is again a recap of what I mentioned earlier. So for me, I did have some preconceptions of what functions meant, what mappings were basically, and that kind of prevented me from understanding what category theory, because you try to generalize what you know as a concrete implementation of category theory. The other thing was the terminology. If we just go back to the next to this one. This is what I came across when I was trying to just find what a category is, and there could be so many different meanings to it, and each of those have got a different meaning in our world. Like, it could mean a class, a group, head, list, set. Each of these have got, and we can in fact interpret category theory in each of these different terms. So if we go back here, the terminology, that was another thing which, according to me, that's one of the blockers that we have when we try to go ahead when we try to learn or learn something more about category theory. The last one was, I think it's more of my personal problem that I've had. Like it's about trying to, when you try to come up with a concise stand-up update, basically, it's really hard to decide what to leave out and what to cover, so that you make sure you've conveyed the message effectively, but at the same time you've not really taken up a lot of time. So I feel abstraction is not as easy as it sounds. As an abstraction, making sure abstracting at the same time, making sure you've got just the right amount of information that you need at that level. So I guess this is something most of us would be familiar with. So these are just concepts from set theory, and we've got three sets. A function from A to B, and a function from B to C. And then we've got the composition of that from A to C. Now, this same diagram can be interpreted at different levels in category theory. You could treat A, B, and C as sets themselves, which would be the category of sets. And then you could treat A, B, and C as any collections of objects, basically. Or it could be a collection of functors, or any mathematical object. And every time we abstract, we go one level above the level we are talking about, like from categories to, let's say, functors, or from functors to natural transformations. There are some of these rules which those patterns have to obey, like composition. And this is one pattern which we would keep seeing as we keep applying these patterns to levels, as we abstract one level above that and move on from there. So yeah, so this is just the terminology which I wanted to cover before we move on. So category, we tend to think of sets, categories as sets, but that's not necessarily what the categorical view of it is. It could be any collection of or any system of objects, or anything, basically, and which there could be a certain criteria which holds them together. It doesn't have to be defined as a set, or a finite or an infinite set. Functors are basically translations from one category to another, or it could be to itself. That's when we call it an endofunctor. But for the purpose of this slide, it's just a functor which maps one category to another category, and categories could be any bunch of things which we talk about. Natural transformation, now this is where we see the same pattern coming up, or showing up again, which is we were talking about functors which are translations between two categories. Now we are talking about translations between two functors themselves, which are natural transformations. Now, of course, that's we won't be seeing natural transformations today. So this is what from the mathematical definition of category. This is what we need to have in a category. So we need to have a couple objects, or some more, maybe one or more objects in there. It could be even a zero, so any number of objects, basically. And we need to have some arrows between them, which I think we generally tend to call them functions as programmers. And there has to be some composition, defined between them. And here we can see that there is an arrow between A and B, and there's an arrow between B and C, but then we can also compose those two together, and we can have a direct arrow from A to C. There's also some laws that govern what constitutes a category. One of them is associativity. So the way you compose the functions or the way you group them doesn't matter. The order matters, but not the way you group them. And every object needs to have an identity. We'll see what this means in probably the next slide. What it means is every object should have a way of getting to itself, kind of like a no-op morphism or a no-op function from itself to itself. Now this is one way of thinking about category theory in what we do. So we could think of each of these types that we work with, ints, doubles, strings, and as individual objects in this category. And we have these morphisms between them. So 2-double would take you to a different object, and then 2-string would take you to a different object in the category. But then you can also compose the two together. You could say, you could do a 2-double first and then apply a 2-string on it. But then at the same time, you can go from an int to an int, or a double to a double, and a string to a string. And that's what identities are. Functions, function composition in Scala, we would generally do that with using the and then on every function. But it only works for single parameter functions. So you then have to curry the function in order to be able to apply that, apply the and then onto it. So this is where we come to the first mathematical structure from category theory. It's a very simple structure. It's a category with just one object in there, and it defines. It has a composition operation which is defined. So it's not just the collection of objects. It's the collection of objects plus an operation which needs to be defined on it. Now, what this means is any category that you could think of each object in that category can be thought of as a monoid. Like in this case, we could think of double with any function that would work on a double as a monoid. A string with any function that works on from string to string as a monoid. And so we do use these concepts on a day-to-day basis, but it's just that when it's formalized in category in a mathematical language, it sounds a bit more complicated than what we are used to. So a monoid is nothing but an object with morphisms from itself to itself, and you could have monoids of each of these types could form a monoid, or you could even have a monoid of one category itself. It depends on at what level you define the monoid. So Cats has this. Cats has a trait which called the monoid, and of course we can. There's much more to it than what I've put up here. But what's important to us is every monoid needs to have a way to combine them, and that's what we mean by composition. And it needs to define an empty value as well of that, and that's what we would need to define the identity. So how do we use this? So if we want to, one of the things that we need to define is the combine. That's the composition, and how you combine is up to you. It's basically that's what because we are defining the category here. So it's up to how we want to implement the composition. So in this case, we have an order, and we're just combining the items in 2 different orders into one, and combining the totals as well. You could be doing anything there, whatever would get you to one order from 2 orders. And yeah, so there's 2 ways to represent it. You could use the catch syntax, or you could even do a combine, like explicitly calling the combine function on it. Next, be talking about functors, and as I was saying earlier, that functors are mappings between 2 different categories. Now, we did see something similar at a much lower level, which is morphisms between objects. And this is a similar pattern again. Now f in this case is a functor between a and b. But what it does is it translates a to 1, b to 2, and so on. So a and b in this case would be categories. So any mapping between there are some more rules to it, but in general, any mapping from one category to another, it could be itself as well, is a functor. There are some rules to it. It needs to preserve the morphisms or the arrows in the original category into the so in this case, if there were any morphisms in A, like the identities, if not anything, at least identities have to be there in every category. So those have to be preserved in B as well. And functors need to compose as we have seen earlier with morphisms as well. So it's the same. It's a similar pattern we are seeing again here. So in functors are not new to us. It's something we've probably seen right from the time we've started working with Scala. Some common examples are lists, options, futures, and this is not something you need to use a library like Cats or Scala Z to work with. Of course, there's no predefined class in the standard Scala distribution, which by the name functor, but it does for all practical purposes, what we need in a functor is it needs to be able to define how a map would work on it, basically how it would compose with other chain computations. So in this case, the example we have is just a list and a function which takes an int and translates it to a string. And what it does is it gives you a list of strings instead. And an option which then converts it to a list of characters. So a function basically would read. Now, if we look at these 2 examples here, what we would see is the order of the list is preserved as when we once this computation is run, and that is something which is very important in a functor. We need to preserve so in this case we could think of the order as the morphisms between one and the other, one element and the other element of the list. So yeah, similarly, even in the second example with the option of a string, the result of this would be a list of characters in the same order as they were put in. Again, as we had a monoid in Cats, we do have a functor as well, and again, there's much more to it than just the map method. But what's important to us when comparing it to the theory is the map method. And that's the only thing we need to define in the functor in order to make it make it be able to chain from one computation to another. One thing we need to ensure is that the types line up when we have functors, or when we map functors. So in this case, we do have a function which goes from A to B, and anything that chains onto this has to start from a B and then move on to a C or something else. This would be how we would use it in case of a functor, and as we can see, this is probably a very trivial example. It doesn't really, we don't need to do this in Scala. An option already has a map method on it, but this might be trivial enough to make it for us to understand what we really need to do when defining our own functor. And in this case, all we are doing is calling the underlying map on the option itself. So, and that part could be whatever we want our composition to look like. So another way to look at functors is the functions in Scala. And this is something I've already mentioned earlier on, that functions, you can map functions from, as long as the types line up, functions can be mapped to or chained together, and we would generally do that with and then. Scala doesn't really have a map on a function, but the and then does the same, or gives the same result. Again, it just works on single argument functions. The reason for that is, I'm not sure about the actual implementation reason for that, but lambda calculus doesn't really have any support for multiple arguments, and the way you do that and do multiple arguments in lambda calculus is you curry the function, and then you provide the second argument, and so that's how you would think of multiple parameter lists. So we could do that using the curried. It's a bit ugly to use the curried and then provide the second parameter and so on, but it does work, and it can be used in an example similar to what's here. So we just taking a function which goes from int to string, and a function which goes from string to a boolean, and then we are composing the two. Now the other way, like I wouldn't be able to call is1 char before I call add1, because the types wouldn't line up in that case. So that's something which is very important when composing multiple functions. There is a number of different types of functors. There's a whole family of functors, and each of those have got different purposes. There's a link I've got in the references, which is a talk which was done a couple of years back on different functors, different types of functors, and what they could be used for. So we have a functor called applicative, and you would hear the terms like applicative functor or just applicative, and it's kind of similar to a monad. I didn't want to touch up on monads today, but it's just one. It's sort of a weaker abstraction on top of a monad. What it allows you to do is it allows you to combine multiple contexts together. So if you had, let's say, so one of the operations which I've used earlier is sequencing multiple options. If you have you have an option of lists, or if you have a list of options and you want to merge them together, so you could use something like that. In this case, you could kind of so sequence would allow you to invert the to invert the context from a list of options to an option of a list. In this case, this is an example I've just picked up from herding cats. I think that's a very good resource on Cats and Scalaz. There's a very good comparison of Learn Your Haskell for Greater Good to what is possible in Scala using these two libraries. This would just convert a list to, it would just convert a list of some contexts to the context with the list inside it. So it just inverts the type. So again, as I was saying earlier, it just combines multiple contexts together. This is very useful when we are trying to do form validation. If you want to, in case of if you want to evaluate each of the contexts individually without breaking at the first flow, because any sort of the other functors, if we go further down the chain, like monads, or they tend to preserve the sequence of operations, that sequence in which the operations are chained. So the first failure would get you out of that chain. But in case of applicatives, we could still have the whole computation done in each context and then merge them together if we want to. So that's the flexibility we get. That's all I have, basically. So these are some of the references some of the resources which I've found really helpful. There's the first talk is the talk by George Wilson is the one which talks about multiple, different functors which generally don't get talked about, and there's some references from Stack Overflow, which it was something I used while trying in order to kind of understand the difference between monads and applicative functors, because that's something I've always found a bit of a gray area as to when would you use a monad and when would you use an applicative. There's a book on cats by Noel Welsh and Dave Kernell, which is also a very good introduction to cats. They do cover some theory, some of the theory part of it, but there are some other references for the theory side of it. But at least as far as cats is concerned, Scala with Cats and Herding Cats are two good resources. And the last one I think is my favorite in terms of category theory, the Bartosz Milewski's blog. And I haven't linked it here, but his YouTube channel as well, which has got a lot of lectures on category theory. And he does talk a lot about the motivations and philosophy and stuff which might appeal to a different audiences. So yeah, that's all I have.